I'd like to welcome everybody to Potential Impacts of Climate Change on Great Lakes Farms and Forests. I'll be your host today. My name is Ann Baird. I'm with Ohio State University Extension in their School of the Environment and Natural Resources. If you experience any other technical difficulties during this webinar, please contact our webinar webmaster, Brian Weaver, by email. That's located in the top part of your chat box, which is on the right side of your screen in the middle. These webinars are an initiative of the Ohio State University Climate Change Outreach Team. This team is working in collaboration with the Great Lakes Regional Water Program in NOAA. The outreach team is a multi-departmental effort within the university led by OSU Extension, Ohio Sea Grant, and the Bird Polar Research Center to help localize climate change for Ohioans and Great Lakes residents. A few logistical aspects for today. During our presentation, all participants will be in a listen-only mode, but you can pose a question for our speaker at any time during the chat box. At the end of the presentation, we will conduct a question and answer session, but you can enter the questions throughout via that box. You can send them to me, the host, or to all participants. We have more than 200 participants were registered for this webinar, a very diverse group representing public and private organizations from the Great Lakes region and beyond, and I want to welcome and thank you for attending. As a reminder, this webinar is being recorded and will be posted on our website for later viewing, along with educational resources and other webinars. Without any further delay, I'd like to introduce Dr. Brent Sanjan, professor with the Department of Agriculture, Environmental, and Development Economics here at The Ohio State University. Welcome, Brent.
Thanks a lot, Ann. I appreciate that, and I appreciate the opportunity to talk with everyone today about climate change and the potential impacts of climate change on Great Lakes farms and forests. Okay, so yeah, here we go. I've been able to switch that over. Let's just get going here. The things I want to talk about today in this presentation are, first off, is talk a bit about trends affecting U.S. agriculture and forestry. We can't look out into the future without thinking about other types of trends besides climate change that might affect agriculture and forestry in our land base, both here in the Midwest and globally. So I'd like to talk a little bit about some of those trends just to give a baseline about what agricultural and environmental economists are thinking about future demands for land, for both forest and farmland. And then turn our attention towards climate change. That's certainly going to be an impact, something that will be affecting production of crops, land values, where and how we produce different kinds of outputs from the landscape. So we'll talk about climate change second, and finally, sort of follow up at the end about discussing the role of adaptation and how we might think about adaptation in our local areas. So the first trend to think about is economic growth. As we look historically, and this is not a long historical view, but just since 1980, the past 30 years, we've seen pretty amazing economic growth globally. Obviously, we all hear the story about China and the rise of China and the incredible strides that have been made there in terms of increasing incomes. And you can see that graphically in the conversion from 1980 to 2010 using data from the International Monetary Fund. We also understand that this change is occurring in other parts of the world as well. In South America, for instance, Brazil, Argentina, and large swaths of South America have seen dramatic increases in income. Large parts of the world have gained in income, and this can have large effects on our agricultural and land base in the U.S. in the future. As we look towards the future, some estimates of how those trends might play out for the next 20 to 30 years. These are estimates from the Energy Information Administration of the U.S. Department of Energy. Basically, their projections suggest that economic growth outside the OECD countries or the large economies of Europe, the U.S., and Asia could be growing at almost twice or more than twice the growth rate of Europe and the U.S. So, for instance, non-OECD Asia, which is led by China, but also by other countries in Asia, such as Indonesia, Thailand, Vietnam, etc., could be growing at 5.7% per year for the next 20 to 30 years. That's pretty astounding growth rates in total economic growth. South America as well, see growth rates greater than The developed regions had 3.7% per year. This can have pretty important impacts for the demand of different kinds of products in the future. Another trend that we should be thinking about is actually population growth, and we'll think about this a little bit differently. In the sense that population growth is actually slowing right now. We're seeing an amazing demographic transition globally occurring in every continent except for Africa, but also we see it in parts of Africa. Essentially, the greatest growth rates in population occurred in the period 1950 to 1975, but since 1975, growth rates worldwide have slowed down, mostly due to rising income, movement of women into the labor force, and other factors that have very little to do with direct government policy toward population. The implications of this is that rather than seeing a world in the future of 13, 14, 15 billion people, we'll probably see a world of only 9 to 10 billion people by 2050, and not a lot of growth if these trends continue beyond that. So the idea there is that as we have rising income and slowing population growth, income per household will be rising worldwide. We've already seen in North America and Europe a growing middle class. A growing middle class demands different things than poorer populations used to demand. It's likely that we'll see a rising middle class in Asia and Latin America. We've already seen that, and it's likely that we'll see that continue to grow. If you look on the right, this is some interesting information from a study from folks over at Purdue looking at cross-sectionally how we demand different kinds of products. The top line, the brown line, is the line that represents our demand for grains. As we go from lower income to higher income globally, we see that our demand for grains continues to rise, but as a proportion of our total income falls. The blue line, on the other hand, represents the demand for things like housing, financial services, education, and healthcare. Our demand for those kinds of things grows as a proportion as our incomes rise, so we spend more of our income on that. The bottom figure in aqua blue is the line for the demand for meat products. Essentially, meat products become a larger portion of our diet as we go towards middle income, and as we get towards higher incomes, they again become a smaller proportion of our diet, but still the demand for those products grows. The implications of this are pretty astounding if you think about it. They'll tell us that even though we may have fewer people we're going to demand in the future, we won't have as many people as we thought we would have in the past, we're going to demand different kinds of food, probably a lot more meat products. The blue line suggests that we're going to demand different kinds of housing. In the U.S., for instance, we went from the 1950s to the 2000s from 1,600 square foot of housing to over 2,500 square foot of housing on average. We potentially could see the same kind of change worldwide in the future as other people in other parts of the world with rising middle-class incomes demand a different kind of housing service in the future. From the land base, we're demanding ecosystem services from our land as well. And we'll have to think about whether we'll continue to prefer more of those ecosystem services in the future. So thinking of that, we can just look at some trends in the U.S. We have this thing called the environmental Kuznets curve that a lot of people have looked at in economics, suggesting that as income per capita rises, we demand less environmental degradation and more environmental quality. We've seen this in terms of the trends of, say, for example, CRP land in the Great Lakes region, where we've increased the amount of land set aside from agricultural production and converted it over to environmental production. In our forest land, we've seen the same kind of thing, a movement towards setting land aside from production of forestry resources and production of forestry outputs towards production of ecosystem services. Another sign of income rising is that we're demanding a shift of our land from producing outputs that we usually use in commodity space towards outputs in environmental service space. As we see these changes happen on the demand side, another factor that's affecting us is going to be technological change in agriculture. And this is a story that worries a lot of people. These are estimates from some colleagues of mine here at Ohio State University, where they basically looked at past trends in corn, soybean, wheat, and cotton yields globally. And then they've used those trend lines and projected them forward, and the implications are pretty astounding. If you look at the top line at corn, you can see that corn increases in yield year over year in 1961 were almost 3%. By 1975, it had fallen to 2%. By 2000, to 1.35% per year. Projecting those trends out, we see further declines in yield growth over time. Soybeans, wheat, cotton, similar kinds of trends. The implications are pretty important. As we demand different kinds of products in the future, we'll be demanding potentially a lot more corn and a lot more soybeans to feed animals, and if we're not getting additional yield from the landscape, the only outlet for increasing outputs is going to be to increase our land use for agriculture, and that could have pretty important consequences for environmental services globally. A lot of concern about what could happen with global crop yields in the future without climate change, even just from a baseline perspective. A final concern about land use in the baseline is the issue about policies. Policies are increasing pressure on our landscape. As an example of that, we can just think of the Energy Independence and Security Act of 2007, which put mandates in place for use of ethanol. 15 billion gallons of that ethanol could come from corn-based sources, and the additional amount would have to come from cellulosic sources. There is evidence suggesting that those policies had an impact on land. We've diverted a third of our corn crop from soybeans into corn, or actually a third of our corn crop into ethanol production. And surely this has an impact on the price of corn, and surely this has an impact on how we use our land. This increase in energy prices, the link between energy and food, will increase the demand for land in the future. So just as a baseline set of issues, it's important for us to recognize that population and income shifts will continue to change how we demand outputs from our land. It will not only happen in the agricultural sector, but also affect our demand for wood and our demand for the environmental services. So we've got to think of these things as a baseline. What I'd like to turn to now, though, is looking at how climate change could impact these baseline trends. And that's really the basis of what we'd like to talk about in this webinar today. So the first sort of issue here when we think about climate change and forest and agriculture is that these two sectors, forestry and agriculture, are already climate adapted. These sectors, if we think of the agricultural sector, has had over 10,000 years of adapting itself to climate. Forestry sector, potentially a slightly less amount of time adapting itself to climate, but nonetheless is also a climate-adapted sector. In addition to that, we have to think of agriculture and food security as probably one of the most important concerns related to climate change. All countries would like to be food secure, and of course they'd like to be able to reap the benefits of a healthy agricultural sector. And so agriculture is an important sector to consider with respect to climate change. The factors that matter for the impacts of climate change on forest and agriculture, I'll put them into 5 categories and really only address the first 3 today, are the issues of changes in average temperature and precipitation, or changes in climate, the effects of carbon fertilization, and the implications of adaptation. We'll talk a little bit about changes in variability, like daytime high temperatures, low temperatures, etc. Talk a little bit about extreme events, as those do matter for these sectors. But for the most part, most of the evidence right now is available in terms of looking at these sectors on the first 3 factors: changes in average temperature, precipitation, changes in carbon fertilization, and adaptation. Okay, so one of the first place to start is to just look out globally at some evidence from this is actually a pretty interesting study by William Nordhaus of Yale University. Basically, Professor Nordhaus went out and looked globally, and for 1-degree grid cells around the world, calculated the amount of output, the economic output in each of those grid cells, and then essentially plotted the economic output in those grid cells on the scale that you see on the right according to the average temperature for the grid cells. And if you look, you see that in colder places, output is a little bit lower, that is economic output, and in warmer places, output is a little bit lower. And there seems to be a global optimum temperature of about 12 degrees centigrade based on looking across all those 1-degree grid cells globally obviously only over terrestrial areas. What this means is that if you get an increase in temperatures on average globally, cooler places could potentially do better because they'll be moving up the curve from the left, and warmer places potentially would do worse as they sort of move down the curve on the right. So this puts cooler places, the places that are cooler than 12 degrees C, in potentially good light with climate change, and places that are warmer than 12 degrees C in potentially bad light with climate change. Right now, if you look at the graph on the bottom, this is data I just took from the FAO. Great Lakes states are slightly colder than 12 degrees average. I think I should be able to do this here. If we look at this sort of color, the brownish type color, that contains the 12 degrees average temperature. Any of these further north are cooler than 12 degrees temperature. So looking and using the data prepared by Professor Nordhaus globally would suggest that, in fact, actually climate change for output from the landscape in the U.S., and in particular in the Great Lakes state, could provide some benefits just by a slight increase in temperature. Why is this? Well, one reason why this is if we look at agricultural outputs, and this is estimates or data from the Intergovernmental Panel on Climate Change. The Intergovernmental Panel on Climate Change has put together, they reviewed a lot of different studies and assessed the implications of yield for a number of major crops. So what we see here are estimates of yield changes with slight increases in temperature. So the x-axis on both of these graphs is an increase in the mean local temperature. The top two graphs are for maize. The bottom two graphs are for wheat. The left graph is for mid to high latitudes, so places that are fairly cool on average. The right graphs are for low latitude regions or places that are fairly warm on average. The key issue here that you see is that when the IPCC looked at the evidence on how yields might change with increases in temperatures, for corn or maize in the mid to high latitude regions, we saw an area from 1 to 2, maybe to 3 degrees where there could be a slight increase in the yields of corn, up to about 3 degrees increase in temperature centigrade. On the other hand, in the low latitudes, there would be very little impact on corn yields for about 1 to 3 degrees, and then increasing losses in corn yields as you went to higher temperatures beyond that. The green lines are with adaptation. The orangish lines are without adaptation. So obviously, if we don't have adaptation, we're much worse than if we do have adaptation. Wheat yields showed substantially stronger increases in yields with increases in temperatures in the mid to high latitudes, and in the low latitudes, increases in temperatures would have a smaller beneficial effect and could have large negative effects as we got to higher and higher temperature increases. So this kind of illustrates the results, I think, a little more strongly than maybe potentially the results from Professor Nordhaus, suggesting as to why we get an increase in output with slight increase in temperature in mid to high latitude regions. Agricultural crops, to some extent, would gain with increases in temperatures where they're grown in cool places, potentially could lose where they're grown in warmer places. So as we look at the data we have right now, it does suggest that in cooler places, i.e. places like the Great Lakes, agriculture could benefit slightly for slight warming, and if warming gets too much, could potentially lose. So going forward, there's a number of major studies that have been done on agriculture in the U.S., and I want to look at those for the next few slides. The first really big major study by Adams et al. In 1990, published in Nature, suggested that there could be somewhere between a negative 10% and positive 10% impact of climate change on agriculture in the U.S., and the biggest reason why there was a big range there was due to the climate scenarios themselves. Mendelsohn et al., however, took that and said, well, let's look at adaptation and try to account for adaptation, which wasn't as strongly included in the Adams study. And they did an interesting study, so let's just show some of the results from that. Essentially what Mendelsohn did is they took average farmland values from the U.S. Census of Agriculture on a county-level basis and did a regression analysis where they related average farmland values to temperature, precipitation, soil quality, and a bunch of other characteristics of the landscape in those counties. And then they used that model to then predict the change in farmland value with a change in average temperature. And the results from that were fairly astounding. So this is the picture that really basically represents the positive 1.2% change in farmland values with climate change. And it's basically with a 5 degree Fahrenheit or about a 2 degree centigrade increase in temperature and an 8% increase in precipitation occurring equally in all of the counties of the U.S., and basically suggesting that in places like Ohio, Indiana, warmer parts of the Midwest, we could have a slight increase in farmland value due to that modest increase in temperature, up to 2 degrees centigrade increase in temperature. As you move further north into places that are currently cool, we can see bigger increases in agricultural land value as a result of climate change. So taking the results that Nordhaus showed earlier and these results, they suggest that, in fact, actually there is evidence that with the way agriculture is currently adapted to climate, that some places that are currently cooler than optimal could benefit from climate change. Places like the lower Great Lakes states, which are sort of closer to the optimal or closer to that 12 degrees centigrade, could potentially not gain a lot but not lose a lot. Obviously, places further to the south could potentially lose as they get warmer with climate change. After the Mendelsohn study, there were several other studies that added another unique feature that was pretty important, has been shown to be pretty important, and took some of those results and reversed them. So the Adams et al. 1995 study and the Riley et al. 2003 study are fairly large market models that incorporate the effect of prices. So if you look back at Mendelsohn, they basically just looked at land values and didn't account for the fact that productivity of land could change, the amount of output from different types of crops could change, and the price of crops could change. Adams et al., Riley et al. Actually incorporated price changes associated with output changes, and the Riley et al. Numbers are pretty interesting. I'll show a picture of those as well. Those show a larger negative range of potential impacts, and this is for the U.S. as a whole. And the interesting thing there is in their study, production of outputs actually increases, but the loss of value in farmlands is caused by the decline in prices as a result of the increase in production. So this is an interesting addition to for us to consider is that markets actually can affect outcomes here as well, and the markets can potentially have a negative impact. So if we look at what happens in the Riley study, we see that actually output in the Midwest increases across the scenarios that they project. Output in the South actually decreases, but output throughout the rest of the country increases. So crop outputs increase in most of the regions. What this does is causes a reduction in prices for many of the crops, and that reduction in prices causes a negative impact for landowners. So in addition to just thinking about how land might be affected by climate change, we also now have to think about how climate change might affect prices for outputs and how that affects the welfare of landowners. There's actually been a recent sort of genesis of a lot more studies looking at climate change impacts in agriculture, and so I want to go through a few of those a little bit more briefly. So the first one is this Schlenker et al., and that was actually started off kind of a new volley of estimates into climate change impacts in agriculture. What Schlenker did is they recognized that the Mendelson et al. Study may have been misspecified because it included all the counties of the U.S., including, for example, irrigated crops and non-irrigated crops. So Schlenker et al. Said, we really should think of the western U.S. and the eastern U.S. separately. So Schlenker et al. Just looked at the eastern U.S. and calculated the same kind of model as Mendelson, but looking just at eastern U.S. states. And when they narrowed down the number of counties in their analysis and narrowed down to a more similar set of counties, what they found is that climate change could actually have a negative impact on crop outputs with their newly specified and different model. In addition, they, as we recall from the Mendelson studies, they did sort of an average climate change effect for every county. So every county in the U.S. got the average 2-degree change and the average 8% precipitation change. Schlenker et al. Actually measured impacts with one of the global the general circulation models, and so they had different impacts on temperature and precipitation changes by county and bigger temperature and precipitation changes by county, so they get a bigger range of negative impacts. After that, Deschaines and Greenstone also commented on the Mendelson piece and said that they misspecified their model. They calculated a new model and actually showed that, in fact, they were more along the lines of the earlier Mendelson results, suggesting that the average effect would be about a positive 1.3 billion effect. More recently, Mendelson and his colleague Massetti have re-estimated the model using some of the techniques from Deschaines and Greenstone, and have actually found a positive effect as well, more similar to their earlier results and less similar to the Schlenker results. So let's go on and talk about a few more impacts in agriculture that we can see. So one of those is that what we know from all these studies, every single one of them point out that adaptation is critical. What we produce is probably going to change and could change potentially dramatically, as we'll see in a second. So Otto During at Purdue University and a number of colleagues there wrote a book in I believe it was 2002 and pointed out that there are maximum temperature thresholds associated with most Midwestern crops. So if corn crops, for instance, experience days above, say, 35, 38, something like that degrees centigrade in the summer, that can have a big negative impact on corn yields. Schlenker and Roberts took this kind of information and then estimated a model using 50 years of crop yields from U.S. counties and estimated what those thresholds were for corn, soy, and cotton. And their results actually indicate that, in this region, in the region where we're located, corn and soybean yields could decrease 20 to 30% by 2020 to 2049, just simply because we're going to experience more days above these temperature thresholds. Say, for example, for corn and soybean, by 2070 to 2090, we'll experience quite a lot of days above that temperature thresholds. So without adapting varieties, without adapting the types of crops that are grown, we could experience some fairly substantial reductions in corn and soybean yields. So Schlenker and Roberts didn't really account for technical change or adaptation, but do point out that adaptation will be critical because we're going to have to deal with these fairly important temperature thresholds for the crops that we're currently growing. Okay, so just to summarize some of the points that emerge from these economic studies of agriculture, the first point is that adaptation is critical. All the studies stress this. A second point is that adapting to weather is different than adapting to climate. This is a really important point made by Massetti and Mendelsohn, and I think emphasized in the literature. So, what do we mean by the difference between weather and climate? Weather is something that farmers actually already deal with. They deal with a lot of uncertainty from weather, and there's actually a lot of really good instruments available to handle that uncertainty within the agricultural community. For instance, farmers can contract their crops forward. They can buy crops from other people when they have a problem with their own crops. They can do a lot of things with financial instruments in terms of forward contracting, hedging, etc., that historically haven't been available but have become more available in the last 25 to 30 years and provide a great sort of adaptation tool for weather effects to farmers. In addition, there's the emergence of crop insurance. Another area where farmers have an ability to deal with weather is through retained earnings. In other words, some of their assets can be used from year to year, and they can get loans based on those assets from year to year, depending on whether they have good outcomes or bad outcomes. And a final thing, which is well known across all agriculture with respect to adapting to weather impacts, is diversification. Diversification can help avoid the big highs and the big lows. So farmers already have a lot of tools available to deal with weather uncertainty, and it is possible that weather uncertainty will change in the future with climate change, but one would expect that many of the current instruments that are already used to be used to help them deal with those changes in the future. Adapting to climate change, though, is slightly different. Adapting to climate change will require thinking about shifts in long-term averages. And this, I think, one would argue, is something that most of us aren't actually going to see. Most of us aren't going to recognize it happening as it happens. We already see that farmers are adapting to new varieties, are shifting from 60-day corn to 80-day corn or whatever as over the last 25 to 30 years in different parts of different states. And what we'll see is that people will continue to make these kinds of adaptations relatively slowly, relatively innocuously, and without a lot of observation by those from the outside. Farmers ultimately will take on new crops, but that's going to occur pretty slowly in this region. So, you have to think of the difference between weather and climate when thinking of adaptation. We have a lot of opportunities to deal with weather impacts, and certainly climate change will cause potentially more uncertainty with respect to weather impacts. But we have some instruments available to help with that, and we'll probably hope to see that those instruments will continue to exist in the future, and we'll probably develop new instruments to deal with weather uncertainty in the future. Climate change, though, is a slower, longer-term shift in outcomes, in average outcomes, and we're going to see changes to the agricultural systems in places like Ohio, Indiana, Illinois, Michigan, etc., but we're not going to see those as obviously as we see adjustments to weather. And the evidence suggests that adaptation could, to some extent, be beneficial for farmers in adapting to climate change, and obviously weather impacts already have large negative effects, and with climate change, those could also have large negative effects for farmers. A final point that emerges from the economic studies of agriculture is that markets are really important for adaptation. The role of prices is vital. It's a huge component for any adaptation strategy. In fact, actually, that's probably how most adaptation will occur. Farmers are going to start to adapt to changing prices for different kinds of commodities and adjust what they plant as those prices change. And that will be as important as weather effects, I think, in the future. And a final point is that beyond just farmers adapting, markets, and that's the rest of us, will benefit from ensuring free trade in agricultural commodities. So, for example, if the Midwestern U.S. does become more vulnerable to large-scale uncertainty due to weather, it's going to be in our best interest to have good open access to international markets for trading commodities because we would hope that other regions wouldn't be susceptible to the same kinds of climate variations in the same direction in the same year. So we'll all benefit, I think, not just in the Midwest, but globally from trying to ensure that we have free trade in agricultural commodities to help minimize some of the large disturbances from potential weather impacts. Let me shift attention to forests and forests in Ohio and the Great Lakes states. So forests will be affected by temperature change, precipitation, carbon fertilization. And again, we have a lot of uncertainty in these effects. And so I just want to go through some of that uncertainty here quickly. If you look across the sort of x-axis here, we see uncertainty in economic outcomes. So these are projections from the Intergovernmental Panel on Climate Change on future economic growth, future carbon emissions, future population growth, etc. Looking down the y-axis, we see uncertainty across the climate scenarios itself. So we see for the Great Lakes region, we can see very big warming under this MUROC climate scenario and A2 future economic scenario to very modest warming under the B1 scenario and the CSIRO climate scenario. We can see drying, substantial drying in this A2 scenario with MUROC to the region getting much wetter under B1. So there's lots of uncertainty in how these temperature change, precipitation change, and carbon fertilization, temperature and precipitation changes will occur in the Midwestern region, and that makes it difficult to predict just how forests will be affected by climate change. I want to make one point on carbon fertilization. In the literature, there seems to be evidence now that climate change, that carbon fertilization will lead to an increase in the growth of trees. So I take this from Nordhaus Study, 2006, Proceedings of the National Academy of Sciences, and that's based on the 4 different FACE sites or free air chamber experiments, where they looked at increasing carbon dioxide in actual forests in the ecosystem, and looking across those different sites where they did this for different forests in different parts of the world, they found that a doubling of CO2 led to an approximately 26% increase in NPP. So it does seem that carbon fertilization could benefit forests even if temperature and precipitation are leading to a drying and harms to forests. So how will these temperature changes, precipitation changes, and carbon fertilization affect forests? They could affect the rate of growth of trees, either increasing the rate of growth of trees or decreasing the rate of growth of trees. Obviously, they also could impact disturbances. We don't typically see forest fires in the Midwest, but if forests get drier, we could see more forest fire impacts in the Midwest. The thing probably people are more worried about are ice storms. We've seen some pretty major ice storms in the Midwest in the past, and we could see these happening with greater frequency. So rather than snow, we could see precipitation in the winter in the form of ice, causing large-scale damages to large swaths of trees throughout the Midwest in the future. So disturbances are an important component of temperature and precipitation changes in the future. As these changes occur, we'll see changing competition across tree types and shifts in species ranges. So these are from the forest atlas maps of the USDA Forest Service, suggesting that, in fact, actually we could see a fairly substantial increase in the range. If you look at the dark green here, basically being oak hickory types, fairly large expansion of oak hickory types into northeastern U.S. Over time, under many of the climate scenarios, and particularly under the high climate scenarios. So we could see fairly substantial changes in the range of species over time due to changes in rates of growth, changes in disturbance patterns, changes in competition across different types of species in this region. So where are we with the now? The analysis of forestry is substantially different than the analysis of agriculture. In the analysis of forestry, we're stuck with taking these scenarios of future climate forcings, linking them to general circulation models, and then getting predictions from ecological models, and then translating those into economic impacts. So whereas with the agricultural models, we were able to sort of directly estimate the effects of climate on current outcomes and use that to infer something about future outcomes, in the case of forestry, we don't have as much data on forest outcomes related to current climates. So we have to use a different approach in terms of linking together different kinds of models, starting with general circulation models, moving to ecological models, and finally moving towards economic models. So I want to walk through just some of those results that we have right now, starting with these ecological models. So this is 2 ecological models. One is a U.S.-based model from the USDA Forest Service in Corvallis, Oregon. Another one is a European-based model, Loon Potsdam-Jena model, basically developed by folks in Europe. Both these models have been used to project changes in forest cover over the next century as a result of climate scenarios. So on the left, in this first set of climate scenarios, we see by 2030 projected changes in forest types under both of these models for 1, the Hadley model, and 2, the Canadian climate model. And what we see in this particular region is that, for the most part, forests seem to expand. We see a conversion from yellow, which would be non-forest, to forest types by 2030 under both the Hadley model and the Canadian climate model. The European model shows a similar kind of result, although it actually shows some drying effects, and these brown areas are sort of woodland savannas, so potential negative effects in this region by 2030. However, by 2090, we see a broad expansion of forest types, in particular this sort of oak hickory type further to the north under both of these models. So by the end of the century, we see a substantial increase in the area of oak hickory, a displacement of our northern temperate deciduous forest, and a displacement of some of our spruce and fir forests, and a definite displacement of our maple beech birch types further to the north. So, if we look at these ecosystem models, there's going to be potentially large impacts on land by the end of this century as projected by the ecosystem models without humans. If we look at integrating the effects across those ecosystem models, what we find is a slight difference in the two models, and I just want to focus on this right-hand side. And basically, this is whether these forests become a sink. So in this case, this large area suggests that there's actually additional growth in forest according to the Hadley model. From those same pictures we just saw, large additional increases in carbon in forests, so that forests are becoming substantially, they're growing quicker, they're becoming a bigger part of the landscape, and we're getting more productive species in the Hadley model. The Canadian model actually suggests more drying, and in fact, actually, forests are a sink going out into the future. So there is a lot of uncertainty across these models, across the ecosystem models, in terms of the impacts on forest ecosystems in the future. Now, the problem is that all these ecosystem models leave people out and they leave markets out. And we have to account for the fact that people will adapt. They'll adapt in lots of ways to all of these effects. One way they'll adapt is through adaptation, by salvaging from dieback or disturbance, by preemptively harvesting as growth rates change, by regenerating new species as climate changes, or by altering their thinning and competition management. Some of these changes are going to be in direct response to climate change, but others will be in direct response to external conditions such as price changes. So let me go through some economic results that we have so far. So taking some of those ecological results we saw earlier and projecting economic output. So this is a set of estimates of, from 2005, some work I did with a colleague, Roger Sedjo, projecting the future of sort of outputs from timber in North America. And I put in red, those two red types are species that are particular for this region. So this red line here is the temperate deciduous forest. The red line here is the northern conifer forest, so spruce and fir type forest. These are two different scenarios of the outcomes. One is a dieback scenario that accounts for the fact that potentially trees could die back as a result of climate change. And what we find for all of North America in the dieback scenarios is an additional 1.6 million hectares of dieback per year, so a large increase in dieback. The regeneration scenario is much more moderate, doesn't have as strong of an impact. Now, in both of these scenarios, what we find is that in the long run, temperate deciduous forest output of timber products actually increases. So what we could see in this region is an increase in sort of the northern hardwood types and outputs from those types over time. And that occurs in both the dieback scenario and the regeneration scenario. However, in northern conifer forest, spruce fir type forests, what we see is that in the regeneration scenario, modest to no impact in the near term, and in the long run, a reduction in that output as that forest type is displaced by temperate deciduous forest. However, with the dieback scenarios, we see potentially large negative consequences in the near term. So if climate change does cause large-scale negative impacts in the near term through dieback, such as forest fires, a lot more impacts from ice storms, etc., we could see large negative consequences in the near term. Now, translating this into economic outputs, what we find is we have to think about what happens in the rest of the world. So what I've done is taken those same results and shown the change in harvest for North America or the change in harvest for the rest of the world. And what we find in both cases, both the regeneration scenario and the dieback scenario, is that output of timber products increases dramatically in other parts of the world. And what this does is have a large negative effect on timber prices. An increase in output reduces timber prices. That reduction in timber prices, because those prices fall by 10 to 15%, leads to an approximately $1.4 to $2.1 billion negative net effect on timber markets or on timber landowners in the U.S. nationally. So even though outputs potentially grow in the U.S., for example, in the regeneration scenario, U.S. landowners in timber markets or timber landowners could potentially be negatively affected by large increases in output in other parts of the world. So an important point there is that the role of international markets can't be left out of consideration when we think of the impacts on land in the U.S. What happens globally with climate change can be as important through its effects through markets and through market prices as what happens here in the U.S. This just puts those impacts, those of course were national impacts, and what we find is that for the most part those national impacts are negative in the southeast and the northwest, and the reason is because those are the two biggest timber-producing regions. For the most part, what we find is that in the Midwest, we would potentially gain on net from climate change over time. So as a final result that I wanted to talk about is we've taken some of this together and working with colleagues at Oregon State, Andrew Plantinga, we've taken some of these results. What we've talked about so far is the impacts of climate change on agriculture, impacts of climate change on forestry separately. Dr. Plantinga has an excellent model of land use in the U.S., and what we've done is applied these results to both agriculture and to forestry and tried to assess the effect of climate change on land use in the U.S. over time. And so we've made projections starting from 2002 to 2052. And the most important point here is to recognize that climate change, I don't have those results very well specified on this page, but climate change actually turns out to be a fairly small impact on the landscape. The big impact, as you can see, is on our increase in urban land uses, in particular in the Midwest, going from 17 or 18 million acres of land in urban land uses today to 50 million acres of urban land uses in the future, with lots of that coming from agriculture, lots of it coming from forests. The biggest impact in the future, at least according to these results, is not going to be from climate change, but it's going to be from our changing demand for land from entirely other forces such as urbanization, etc. So in summary, this is just a summary slide with some of the results that we've seen so far. If we look at the climate projections for the region by 2030, this region could see 1 to 1.5 degrees centigrade increase in average temperatures. By 2090, 2 to 4.5 degrees. Precipitation is projected to increase. Most of that change of increase in precipitation will occur in the winter, not so much in the summer, so not a lot of help for our agricultural crops at least. Agricultural returns, however, are expected to increase modestly from 0 to 2% on average, with the biggest increases in the northern Great Lakes states and much more modest increases in Illinois, Indiana, and Ohio. By 2090, we can see a broader range of negative potential impacts as a result of some of those factors we talked about earlier, that is the large increase in number of days with very high temperatures in the summertime, and that would be expected to mainly impact or have an effect on the southern Great Lakes states. Northern Great Lakes states would probably mostly be in the positive range even by 2090, although probably much more modest than by 2030. Forestry returns in the region are mostly expected to increase between 2030 and 2090 in pretty much most of the ecological scenarios, largely due to, even if some of the species that we currently have are negatively affected by climate change, adaptation to newer species from the south by the end of the century could be fairly important for forestry returns. So there is a lot of uncertainty around these results, but this, in my opinion at least, are some average results based on the studies that we've reviewed in this webinar so far. A final point I wanted to make was just how do landowners use climate change information. I think it's important to recognize that farmers are already adapting. They're changing what they do on a daily basis. They're changing their infrastructure, for instance, adding drying bins, adding more drying infrastructure on farms rather than relying on the marketers to do the drying for them. They're doing different things with their drainage systems. They're doing a lot already to adapt to climate change, and we would expect that they'll continue to do that kind of stuff into the future. It's virtually impossible right now to use specific information from these general circulation models and use it to tell farmers or suggest make suggestions to farmers on what they should do, or to foresters on what they should do. And largely because these climate change projections are very uncertain. Obviously, there's huge uncertainty about our future carbon emissions, and then even the climate scenarios themselves are very, very uncertain. So what that suggests to me is that we should probably we should probably be pretty modest in any of our current recommendations to landowners. By 2030, this might be changing. We might be much more certain by 2030, and so we could be making more projections by 2030 or more suggestions to landowners. However, at the current time, there doesn't seem to be enough information from the climate models to really make specific projections to landowners or specific suggestions to landowners on how they should be changing their land use or their crops or whatever related to climate change itself. Just a few other issues for forest landowners to worry about. Forest landowners have some specific concerns mainly related to the length of time that it takes to grow trees and the fact that that they're managing a pretty important stock of stuff even right now. And some of those decisions are compound. Agriculture is an annual crop. The ability to adapt agriculture rapidly to climate change is probably actually much easier than forestry, which is a long-term crop, has a big stock of stuff that provides both ecosystem services and economic outputs in traditional markets, and it's very difficult to start thinking about making those decisions related to climate change. So, the best approach there is probably the same with respect to agriculture, is that we've got to go slowly. It's probably not enough evidence to start anticipating disturbances yet, probably not enough evidence to start changing exactly what you do with respect to regenerating your forest today, but probably in the next 20 to 30 years we will start to see some modest changes in how forest landowners do manage their forests in response to climate change, but it will probably be pretty modest. So in conclusion, land gets more valuable. The underlying trends in economics, rising incomes, population changes, and policy are going to have big effects on land. Climate change is going to be one impact on that, and as suggested by that result from that last result from Haim et al., suggests that actually climate change might be more modest than some of the other factors affecting land use in the future. And therefore, adaptation will probably be pretty modest in agriculture and forestry over the next 25 to 30 years. However, we'll probably start to see more substantial shifts beyond that. So I think I'll go ahead and stop there and I guess open it up to questions. Thanks.
Okay, thanks a lot, Brent. We've got a number of questions. We'll start with some in the category of crops and land values. The first one we have is, do the potential increases in crop outputs for Ohio also consider climate change impacts on rainfall, evaporation, and severe storms?
Yes and no. So in terms of the precipitation, the current models do account for precipitation changes. If you go back, let's see if I can go back to some of those slides. So this study by Mendelson et al. Accounted for precipitation changes, but assumed an 8% increase in precipitation for every county. So it didn't account for any of the geographical distribution of changes in precipitation projected by any of the ecological models. Somehow I ended up way down there again. Anyways, the other study by Schlenker and Roberts actually did account for the distribution of temperature and precipitation changes according to. They used two different general circulation models, so they did account for those precipitation effects and the distribution of those precipitation effects. And not surprisingly, because they looked at a larger negative range of precipitation effects, they did find a larger negative range of potential impacts on crops. So there is, of course, variety there in terms of the economic results, and some have included precipitation geographically distributed, and some haven't. With respect to storms and other kinds of impacts on agriculture, to my knowledge, there aren't any studies that have looked at the direct effect of storms. The only studies that have looked at the effects of large uncertainties are those that have looked at sort of this possibility of very hot days in the summer, and that's the Schlenker and Roberts 2009 article, and it's also that same phenomenon is referred to in Otto During's book, and that is exceptionally warm days, that is hot, dry spells can have large negative consequences for crops. The forestry literature, of course, has looked at implications of these kinds of things for trees, in particular the effect of large events on disturbance patterns. So that's a little more rife with the precipitation and disturbance pattern impacts.
Okay. We'll switch over to more of an education question. Do you have experience with farmers who are already adapting to climate change? And what, in your view, are the best ways to educate farmers about the most likely coming changes?
Well, I think there's two parts to that question in terms of experience with farmers who are adapting to climate change. And to one extent, any interaction with farmers is dealing with individuals who are adapting to climate, right? They're already growing crops in a specific region because the climate happens to be adapted for those crops, and they're making a lot of adjustments to handle different kinds of factors. So, for example, in the eastern Corn Belt, we see a lot of tile drainage to handle too much moisture. So, at particular times of the year. So that's an adaptation that's already occurring within the region, and one would expect that if we saw more large storm events, we potentially would see a move towards better tile drainage systems that would get rid of some of that storm event, the storm surges associated with that. We'd see bigger ditches, et cetera, as an adaptation. We already see some adaptation towards that in these regions. So I think, while I've never talked to landowners who are specifically trying to adapt to climate change as a phenomenon, we certainly are working with landowners who are thinking about adapting to all kinds of phenomenon, one of which is climate. So we do see that. Now, I think, what was the second part of that question, Ann?
Yeah, and what, in your recommendation, would be the best educational approaches?
Well, I think basically just general education right now, because in my opinion, there's not enough information out there, evidence out there to recommend specific adaptation strategies to climate change. However, we probably should continue education on the existing ways to deal with weather effects and weather events and things like that, because being able to use hedging strategies, to use insurance contracts, to diversify your farm operation, those kinds of things, which are already really important for how we handle large-scale weather effects in farming, are going to continue to be important and become more important. So continuing to educate on those, I think, is probably the most important thing we can do for climate change right now.
Okay, we'll skip down here to some approaches to address these issues. A little outside the, just on your thoughts, do you feel the current state of subsidies in Ohio and the Midwest may hinder the ability of agriculture to adapt to climate change?
That's an interesting question. There's been a little bit written on that in terms of subsidies and agriculture and climate change. So one notion is that subsidies could potentially cause bigger damages because the agriculture sector is bigger than it would otherwise be with the subsidies. So it actually could make climate change more harmful in the agricultural sector. On the other hand, you could think of that as if the sector is bigger than it needs to be, output's bigger than it needs to be, then probably we have a little bit of a cushion if climate change does start to cause some negative impacts. So, the subsidies themselves, do they make it harder or less difficult, or more difficult or less difficult to actually adapt? I haven't seen any research on that, and my first instinct is that the subsidies. My first instinct would be subsidies probably would make it more difficult to adapt, in part because they lead you away from diversification. Subsidies, as we have them in the U.S., tend to focus on specific types of crops, and so they would tend to lead you away from diversification and towards specific types of crops. So in that sense, it could be a negative impact. On the other hand, they can provide a nice cushion for landowners in terms of getting them from one year to the next if they do happen to have a bad year, and so that can provide a benefit. Now, the offsetting, whether those two things offset, I don't know. That's a really good question that actually deserves a lot more research.
Okay, we'll switch over to, we had a few questions on models. One was just on the forest community predictions for geographic range distributions. The question specifically was, what accounts for the differences in distribution between the North American and European models, particularly for 1990?
Yeah, that's a good question. I think the key is that the North Americans are good at predicting North America and bad at predicting Europe, and the Europeans are good at predicting Europe and bad at predicting North America. I just think that essentially it illustrates that there's a lot of uncertainty about any of these predictive models, and so they're using different algorithms, obviously, and the algorithms that seem to work best in European forests maybe don't work as well here in the U.S., North America, and vice versa as well. So I think that illustrates the limit to all this modeling for practical purposes, basically.
Yeah, and we'll just take kind of one closing question about this idea of uncertainty and moving forward. The attendee noted there will always be uncertainty, but there's also quite a bit we do know among many models regarding general changes. They would just like to know about your perspective with actually regarding general changes which should be communicated. What is your just perspective on moving forward in uncertainty?
Well, the lesson I take from the current set of models really is that if we want that we should continue to work on making these sectors as resilient as possible by having good tools available for the landowners to adapt. So to me as an economist, I look and say, well, actually markets can help a lot with this by providing price incentives. So in other words, landowners who, if we start to see, persistent reductions in corn crops in the Midwest as climate changes, well, we would hope that, again, there was a subsidy reference earlier, that subsidies would not be too big of a part of the equation, and in fact, actually, that corn prices would start to rise, and that would lead us to do what? That would lead us to invest more in corn, and with less people, it would encourage people at the edges, perhaps further north, to plant more corn rather than wheat. So if we allow prices to change and adjust, and we keep those markets as free as possible, that's going to provide the right kind of incentives for landowners to make better decisions than they could otherwise make. So I guess I take from it that there is a lot of uncertainty out there, and we can't start making specific recommendations to landowners, but we can start we can continue to push some of the existing tools for dealing with uncertainty that we already have, such as the hedging contracts, such as insurance, such as diversification, such as maybe it's tile drainage in one place, maybe it's trying to avoid drainage in other places, i.e. irrigation in other places. So we can continue down the road of those things and pushing landowners to think about those options, but at the same time we can try to keep markets as free and open as possible so that those price incentives can work the wonders that they do in terms of encouraging people to make good decisions or better decisions.
Okay, thanks so much, Brent. I want to thank Brent today and really all of our participants for an excellent set of questions and presentation. This presentation and related education materials will be posted at changingclimate.osu.edu along with the previous webinars in this series. We really would appreciate knowing what you thought of today's program, and Jill will post now a link to an online evaluation that will just take a few minutes that you can let us know what you think and what future programming you'd like to see. And I do want to just remind you that the next webinar in this series will take place on December 7th of this year and address impacts on water quality in the Great Lakes from biological, societal, and economic perspectives. Registration will be, a link to that registration will be sent to you later this afternoon. We do apologize, there was some technical difficulties for logging on using the voice integrated protocol, so we apologize for any delays due to that, and we'll get those corrected for the next one. Again, I want to thank everybody, and that will conclude today's webinar, and we'll look forward to speaking with you again or hearing from you in December. Thanks so much.